All right, I want to talk about the ballistic pendulum. Now, a ballistic pendulum essentially is a device where you can have some kind of a launcher or a gun that shoots a bullet or some kind of projectile, and we want to figure out the launching velocity or the muzzle velocity of the projectile. So, for example, here we have in this illustration, what's going to happen is the projectile is launched or fired from the gun. It is going to impact this block that's hanging and become embedded in the block. And as a result of the impact, the bullet and block will now begin this thing swinging like a pendulum. Okay? And so a ballistic pendulum involves two key physics conservation principles. In the collision, we have conservation of momentum. And then in the swinging pendulum, we have conservation of energy. So those are the two key physics principles and conservation ideas that are involved in a ballistic pendulum problem. So let's take a look and see how we go about solving this. Conservation of energy. So we can do this symbolically, or we can come up with some numbers. I'm going to do it symbolically first, and then we'll look at some numbers and see how we work out some of these problems. So what we have here is in the collision, we have initial momentum equals final momentum, okay? And the initial momentum is just in the bullet, okay? So that's going to be little m times v naught. That's our initial momentum. Then our final momentum after the collision and before the pendulum has begun to swing, they're stuck together. So our new mass is big M plus little m, and I'm going to call this times v. V here is the velocity of the bullet and block system just after the collision. And so at this point, to solve for v naught, we can see it's just big M plus little m over little m times v. That's going to be the initial velocity or the muzzle velocity of the bullet. Okay? Now, in most of these problems like this, what you'll have is the pendulum swings to a height of 2.5 centimeters or whatever, what I'm going to call delta y over here. So as the pendulum swings through this angle theta, okay, it's causing the center of mass of the bullet block system to change its height. So in the swinging pendulum, we know at the bottom we have kinetic energy, and at the top we have gravitational potential. So our conservation of energy equation becomes then kinetic energy at the bottom, 1/2 m plus mv squared, equals the gravitational potential energy at the top, which is big M plus little m times gh, or delta y. I'm going to use h here. So h is the same thing as this delta y, the change in vertical position of the center mass of our bullet block system. You'll note here that the combined mass will in fact divide out, and that the v here is the square root of 2gh. So v here is the velocity of the bullet block system when it reaches its lowest position, and that's where it was when the collision occurred. And so the v here is the same as the v here. So with numbers, if I knew how high it caused the system to rise, for example, I could figure out the v here and use the v after collision over here to figure out the v before collision. Okay? So essentially, conceptually, that's what's going on. Now, sometimes you could see a problem with this ballistic pendulum, for example, where they don't give you the vertical displacement. They don't say, hey, it causes the system to rise by 2.5 centimeters. They might give you a horizontal displacement. So how could I solve for the vertical displacement if I had the horizontal displacement? So we're going to use a little geometry here, a little trig and some geometry to look at a scenario like that. Get a new piece of paper here. So if I have a pendulum, we'll just simplify it like this, and here we go. So the pendulum has swung through this arc, and let's say we know this theta. The pendulum is of length L, and we know the horizontal displacement, I'm going to call that x, and the vertical displacement here is delta y, or height. Okay, so what I do know is that the length of the pendulum from here to here is the same length of the pendulum from here to here. So this height, or this delta y, is equal to the length of the pendulum minus the length of this side of that triangle. Now, that triangle, this is a leg of a right triangle. And the leg is equal to, this is adjacent to the angle, and the adjacent leg is equal to the hypotenuse times the cosine. So this is actually L cosine theta. That's the length of this leg of the triangle. Okay? And so, if this is L cosine theta, then the height, or the change in y, of our ballistic pendulum is equal to the full length of the pendulum minus L cosine theta. That's going to give us our height, or our delta y. So you might come across a situation like that. Now, in a problem where we were given the horizontal displacement, what you could do is you could say, okay, well, I know the length of my pendulum, and I know the horizontal displacement, so I could find the angle. So theta would equal the inverse sine of x over L. And once I know theta, then I can say, hey, the height is L minus L cosine theta. So there's a lot of little geometry and trig ideas that are assumed that you're going to understand as you're looking at a ballistic pendulum type of problem. So let's look at an example with some numbers then. So suppose I have a 3-gram bullet traveling at, we don't know, we're trying to find it, and it's going to strike a block of mass 2 kilograms. That is hanging, suspended, and we'll just go with a simple example here, supposing that it causes a, well, I've used a number before, we'll just go with it, 2.5 centimeter change in height. And we want to figure out what was the initial velocity of this bullet. Well, again, 2 parts to the problem. For the collision, you're going to use momentum, and for the swinging pendulum, you're going to use energy. Okay? It's very important that for the collision, you use momentum. You cannot use conservation of energy and say, hey, mgh over here equals 1/2 mv squared before the collision. Because in the collision itself, a lot of the kinetic energy it has initially is dissipated. And so while total energy is conserved, the dissipated energy is not accounted for in our mechanical energy equations. So I have to use momentum for the collision, and then I use energy for the pendulum. So for the collision, P initial equals P final. That's going to be mv initial equals big M plus little m times v final. So that is 3 grams, so 0.003 kilograms, times v naught, which I don't know, equals m plus m, that's 2 kilograms plus 0.003, 2.003 kilograms times v final. Okay, so v initial equals 2.003 over 0.003 times v. I can go this far if I want to, and I get 667.7. So v initial equals 667.7 times the v after impact. So to find this v after impact, I'm going to go to conservation of energy. And I know that big M plus little m gh, the gravitational energy here, equals the kinetic energy here. 1/2 big M plus little m v squared. The masses, of course, will cancel out. I could put in the numbers there, but they're just going to cancel out anyway, so I'm just going to leave it like that. Canceled out. And I can see that v is the square root of 2gh. So the height change is 2.5 centimeters. So the square root of 2, use 10 for g, and 0.025 meters. This is going to be my v. So the square root of 2 times 10 times 0.025 is 0.7071. So 0.7071 meters per second is the v. I'm going to take that v, that's v after impact, I'm going to plug it in here. So I'm going to take this answer, I'm going to multiply by 667.7, and I then get the initial speed of the bullet is 472 meters per second. And that is how you solve a ballistic pendulum problem.